So next one, output current equations of common base, common emitter configurations. So in that common base configuration, what is the amplification factor? So last class we have to be discussed. So the amplification factor is alpha. What is the definition for amplification factor? Alpha is equal to output current by input current. So see here. So we have to be discussed last class. Amplification factor alpha. What is the alpha is IC by IE. What is beta? Beta equal to IC by IB. Gamma is equal to IE by IB. Okay. Now after we know the relation of alpha, beta, gamma, we have to see the output current equations of CB and CE configurations. So CB configuration. CB configuration. In that, what is alpha? IC by IE. Now, how can we write IC? IC is equal to alpha IE? Yes. Suppose IE is 0, is that output current become 0? No, because IC is a combination of forward bias and reverse bias current. So IC is a combination of, so this is the CB configuration. So this collector current is nothing but combination of forward bias and reverse bias current. So forward bias and reverse bias current. So at that time, what is the IC current equation? IC is equal to alpha IE plus ICB naught. ICB naught. So here collector to base with emitter open. So here in reverse bias, collector to base with emitter open. So this will be, write it as alpha IE plus IC naught also. Because current due to reverse saturation, so thermally generated carriers. So that's why we are able to write ICB naught is equal to IC naught. So come to the CE configuration. For CE configuration, so this is common emitter configuration. For this common emitter configuration, what is beta? So beta is equal to IC by IB. IC by IB. What is the output current equation? IC is equal to beta IB. Same way, when IB is 0, the IC becomes 0. No, not 0, because reverse current is there. That reverse current is emitter to collector. So our collector to emitter. Here the reverse current is there. So that's why, how can you write this as a IC is equal to beta IB plus ICE naught. Beta IB plus ICE naught. So this is collector to emitter with base open is called as ICE naught. So IC is equal to beta IB plus IC naught. Here IC is equal to alpha IE plus IC naught. So this IC naught, this IC naught are equal? Not equal. Why? Because so in CB configuration, so IC is equal to, what is it is? Alpha IE plus alpha IE plus IC naught. We know very well alpha. How can you write IE? IE is equal to IB plus IC. We know very well, isn't it? The emitter current is equal to base current plus collector current. So alpha IC plus IB plus IC naught. So IC is equal to alpha IC plus alpha IB plus IC naught. So you have to send this ICs in this side. What happened? IC minus alpha IC is equal to alpha IB plus IC naught. So here when IC common this thing, 1 minus alpha is equal to alpha IB plus IC naught. Alpha IB plus IC naught. When IC is equal to alpha by 1 minus alpha IB plus 1 by 1 minus alpha IC naught. 1 by 1 minus alpha IC naught. What is alpha by 1 minus alpha? So this is nothing but with respect to beta. Beta is equal to alpha by 1 minus alpha. Beta IB plus 1 by 1 minus alpha is gamma. So gamma with respect to beta, the relation of beta 1 plus beta. So 1 plus beta IC naught. So IC is equal to beta IB plus 1 plus beta IC naught. So when we observe that here beta IB, we observe that IC naught is equal to 1 plus beta ICB naught. ICB naught, nothing but IC naught. So whatever it is, ICB naught or IC naught, both are same. So in CE, reverse saturation current is more than CB reverse saturation current. So here in CB reverse saturation current is CE reverse saturation current is more than CB reverse saturation current. So in CE configuration, current is more. So it has thermal problem, stability problem. So to avoid stability problem, we use biasing techniques. So we have to be observed. So this beta IB plus 1 plus beta IC naught. So IC naught is equal to IC naught. So both are not same. So IC naught is equal to what you get. This will be useful in problems. IC naught is equal to 1 plus beta ICB naught. So we have to be observed. CE configuration has more current. So it has thermal problem, stability problem. To avoid that stability problem, we use biasing techniques. Okay. So in CB configuration, what is the advantage of CB configuration? Thermally stable. CB is thermally stable. CE disadvantage is thermal runaway problem will occur. CE disadvantage is thermal runaway problem will occur. So we have to be observed. In CB configuration, what is the formula? IC is equal to alpha IE plus IC naught. Alpha IE plus IC naught. So IC is in milliamperes. IC naught is in microamperes. When temperature increases, IC naught increases the order of microamperes. Even though increases, so IC naught is in the order of microamperes. So it is not influence for IC. So that's why CB is thermally stable. So when temperature increases, IC naught increases. What happen? IC will be changed, but in the order of microamperes. So that's why it is very negligible. So because of that, CB configuration is stable. So come to the CE configuration. What is the output current equation? IC is equal to beta IB plus 1 plus beta IC naught. Beta IB plus 1 plus beta IC naught. When temperature increases, IC naught increases. Temperature increases, IC naught increases. What happen IC? IC also increases. So IC also increases. So IC increases. How much it will be increase? 1 plus beta times it will be increase. Suppose beta value is 100. So it will be increase 101 into IC naught. 101 into IC naught. So here somewhere when temperature increases, IC naught increases, IC increases and going on, somewhere transistor will self-destruct. This phenomena is called thermal runaway. This phenomena is called thermal runaway. Due to increasing of temperature, self-destruction of transistor takes place. So that is called thermal runaway. So beta, IB, ICB naught all increases with temperature. ICB naught doubles for every 10 degrees centigrade rise in temperature. Collector current causes junction temperature to rise. So what happened? ICB naught rise in IC. This cumulative process lead to what happened? Collector current to increase the further and transistor may be destroyed. So that phenomena is called thermal runaway. So to avoid that one, we have to provide heat sinks. Heat sinks can be used and negative feedback can be built in the biasing circuit. The transistor can be biased so that collector is normally less than the half of the power supply voltage. So it implies collector emitter power dissipation is maximum value. So runaway is then impossible because increasing collector current leads to a decreases in dissipated power. So in this way, we have to take some precautions to avoid the thermal runaway. The next one, H parameters. So we know very well in networks, Z parameters, Y parameters, H parameters, ABCD parameters. But here for our transistor characteristics, suitable one is H parameters. So that's why we have to be preferred transistor parameters of we taken as H parameters. We discussed transistor parameters. In that, we preferred H parameters. So for that H parameters, what is the formula for H parameters? The generalized formula is V1 is equal to H11 I1 plus H12 V2. H12 V2. So I2 is equal to H21 I1 plus H22 V2. So we want to know the H11 value. H11 is equal to V1 by I1. V2 is equal to 0. So this is called, so here the 1 means input. So input voltage by input current. So that's why it is called input impedance. Input impedance. So same way H2 1 is equal to I2 by I1. I2 by I1. V2 is equal to 0. This is called, so gain means output by input. So here current gain. So that is I2 by I1. So that's why it is called as forward current gain. Forward current gain. So H12 is equal to V1 by V2. V1 by V2, I1 is equal to 0. So this is gain, voltage gain, but how it is? Generally, voltage gain is output by input, but here V1 by V2, that's why reverse voltage gain. It is called as reverse voltage So this is reverse voltage gain. So next one, H22. So finally the parameter is H22. So that is I2 by H22. I2 by V2, I1 is 0. I2 by V2, I1 is 0. So output current by output voltage. This is called output admittance. Output admittance. So this equation will be write in transistor parameters. So it will be converted to in transistor parameters. So V1 is equal to H11 means input impedance. So that's why HI I1 plus. So this is H12 is reverse voltage gain HR V2. So same way I2 is equal to H21 is forward current gain, the first letter F, HF I1 plus H22 is output admittance H0 V2. So when we are using CB configuration, so you have to be write it as everywhere B. Okay, one means input voltage, two means output. So wherever input, here we have to write, suppose it is in CB configuration here. So common base, suppose common base. What is input voltage? VEB. Input current IE. What is output voltage? VCB. So what is output current? IC. Okay. So according to that, V1 means VEB. V1 means VEB. I1 means IE. V2 means VCB. So same way, I2 means IC. I1 means IE. So V2 means VCB. So this is common base. According to this common base, HIB, HIB is equal to V1, HIB is equal to V1 by I1. VCB is constant. So VCB constant. V1 is VEB by IC. E by IC. So same way H21 is equal to. So this is the H21 means HFB. So IE by IC by IE. So same way IC by IE HFB. So what is this? H21 is HFB. HFB. IC by IE. IC by IE. VCB is 0. So reverse voltage gain. So this is reverse voltage gain H12. What is? So reverse voltage gain means H12. Here this is the reverse voltage gain. So reverse voltage gain means V1 is VEB. VEB by output వచ్చి VCB. So input current ఏమి IE. IE is equal to 0. IE is constant. You have to write it as IE is constant. So what is H22? Means HOB. H22 means HOB. So IC by V2 means output voltage. What is output voltage? VCB. So I1 is emitter current. IE is equal to constant. So in this way, so you have to write the H parameters of remaining configurations also. Suppose it is in common emitter configuration. How can you write it as HIE? HIE. Okay. So what is common emitter configuration? You have to draw the diagram according to that. You have to write it as HIE-I1 plus HRE V2 plus HFE I1 plus HOE V2. So you have to write it as here HIE, HFE, H reverse voltage gain, HRE, HOE. Okay. So in this way, in H parameters, suppose it is in common base, common emitter, common collector configuration. According to that, you have to write it as H parameters, transistor parameters for common base, common emitter, common collector configurations. Common base, common emitter, common collector configurations. So now we have to be discuss the characteristics of CB configurations. So CB configurations. So see here the output characteristics. So because of input characteristics are just like normal diode, so that's why we have to be discussed here only output characteristics. For this output characteristics, so how the characteristics are draw here. So this is in x-axis output voltage. So this is CB configuration. In CB configuration, output voltage is VCB. So here this is the VCB. So in output current is IC. Output current is IC. So we have to show here. So in this VCB, the output characteristics, output current is IC, output voltage is VCB. So here we have to take an as in x-axis VCB, y-axis IC. Why we take like that? Why don't you take here current and here voltage? Means the current is in y-axis. So that is dependent term. So VCB is in x-axis, that is in independent term. So generally what is the equation for y is equal to mx? Y depends upon x. Y depends upon x. So that's why you have to be taken like this. The parameter input current as a parameter. Input current vary, output characteristics. What happens? So see here. So what is the equation for this? Alpha. So IC is equal to alpha IE plus ICB naught when IE is 0. So IE is 0. So what happens? Some ICB naught is there. When IE is equal to 0, some ICB naught is there. So this is the cutoff region. So this one is cutoff region. So when IE is equal to 2 milliamperes, so IC you have to be taken as 2 milliamperes, 4, 6, 8 like that. So suppose IE is 2 milliamperes. So it will be what happens? So it will be, so IE is equal to 2 milliamperes. So here IE increases. So that's why IC constant. So VCB increases, IC constant. The current drastically increases where it is I is 0, only reverse saturation current is 0, current is there. So when I increases, so drastically it will be increases. So what happen? When IE is equal to 4 milliamperes, when IE is equal to 6 milliamperes. So you have to be observed, IC is 6, some little bit light variation is there because of, we know very well, IC is equal to IB, IE is equal to IB plus IC, IB plus IC. So IE is equal to IB plus IC. So that's why the characteristics will come like this. So when VCB increases, IC constant, CB can be used as a constant current source. CB can be used as a constant current source device. So it will be used in high frequencies. It will be used in high frequencies. So after that it will be constant current source. Why the characteristics will come like this means, so here also the early effect is there, but not for more than of CE configuration. So how the CE configuration characteristics are there? So in CE configuration, output characteristics is output voltage to output current. Output current is IC, voltage is VCE. Okay, so according to that, how can you draw the characteristics? So for this, VCE IC. So what is the equation here? IC is equal to beta IB plus 1 plus beta into IC naught. So here when IB is 0, reverse saturation current is there. So that is, so IB is 0. So when we increase the IB value, so it will be 1 plus beta times. So that's why it will be increases like this. So here the parameter is IB. The parameter is IB. BJT is a current control device. So it is a current controlled current source device. So IB is equal to 0. So VCE, when we have to write the VCE loop equation, current comes IC naught is more. So IC is equal to beta IB plus 1 plus beta IC naught. So IB suppose 20 microamperes. IB is 20 microamperes plus, so here 1 plus beta times means 1 plus 100 into IC naught. So when VCE increases, what happen? IC slightly increases. So because of early effect, the characteristics are comes like this. So when we are increasing the reverse bias voltage, what happen? It will be increases lightly doped side. So it will be increases slightly doped side. So that's why here the effect, the characteristics are shows like this. So VCE voltage increases, base width will be decreases. So IC increases. So what happened? Here the power is increases. So that's why it will be operating only in active region only. So this is the cutoff region. So this one is saturation region. So this one is active region. So this is the beyond region of the active region. So same way here also. So cutoff region, saturation region, active region. So now we have to be discussed differences of CB, CE and CC configuration and which configuration is most popularly used. In CB, CE, CC configurations. So we know very well for CB configuration. So this is CB configuration. So this one is CE configuration. This is CC configuration. So for this, here when it is in active region, emitter base junction forward bias, collector base junction reverse bias. Here also here also. So what happened? It is in forward bias, it is in reverse bias. So what happened? So this is reverse bias, this one is forward bias. Okay. So here the input impedance. So emitter base junction is forward bias. Collector base junction is reverse bias. So that's why the resistance offered low resistance. Here the resistance offered is low resistance. Here input impedance is low, but we increase input impedance. So here the input impedance is forward bias, but we have to be increase. We are able to increase in CE configuration in biasing. Okay. So here output taking across the emitter. So the CC configuration, another name is called emitter follower. So the another name is emitter follower. Output taking across the emitter. So that's why it is also called as emitter follower. This is opposite of common base. So here the because of reverse bias, the input resistance is high. The input resistance is high. So here obviously when input resistance is low, output resistance is high. Output resistance high. So here also high, here low value because of forward bias. So come to the current gain. What is current gain? Current gain is output current to input current. It will be denoted as AI. So it will be denoted as AI. So AI current gain. So alpha is equal to IC by IE. Okay, IC by IE. So suppose it is in DC IC by IE, it is in AC change in current, collector current to change in emitter current. What is the alpha value? We know very well. IC is approximately equal to IE. So the value is 0.96 to 0.99 varying. So nearly unity gain. So it has nearly unity gain. The gain of 0.99 is advantage or disadvantage? Disadvantage. Why? Because 100 rupees you are spending, how much you get? 99 rupees. So it will be disadvantage. So in CE configuration, beta is equal to IC by IB. So IC is in milliampere, IB in microamperes. So high value by low value, it gives to high value. Already you know very well, beta will be vary 50 to 250. So here beta may be 10, 20 like that also. But here the beta value will be vary 50 to 250. So here the current gain is high. The current gain is high. In CB configuration, the current gain is nearly unity gain. In CE configuration, current gain is high. So here in common collector configuration, what happens? IE by IB. IE by IB. So IC approximately IE. So highest current gain in this. So because IC approximately equal to IE, the gain in CC configuration is high. So high by low value, highest current gain. So here gamma is equal to 1 plus beta. So here only beta, here 1 plus beta. So that's why compared to CE configuration, CC configuration has highest current gain. Highest current gain. So come to the voltage gain. So finally it has unity gain. It has nearly unity gain. The gain is current gain is high. Here highest current gain. Here highest current gain. So in this voltage gain. So here in voltage gain, how can you output by input? Output Emi IC R not by input is IE RI. So output collector current to output resistance is high. Input current to input resistance is low. So here this resistance is high, this resistance is low. High by low is high. So IC approximately equal to IE. So that's why these two are negligible. When high resistance value by low resistance value, it is high. So in CB configuration, voltage gain is high. Voltage gain is high. So here also high by low. So that's why here also voltage gain is high. So here the voltage gain is less than unity. So what is the drawback of CB configuration? Input impedance is low, current gain less. So in CE configuration, input impedance is medium, output impedance is high, voltage gain is high, current gain is high. In CC configuration, output impedance low, voltage gain less than unity. So come to the applications where we used in CB configuration for high frequency circuits we have to be used. It is used as an amplifier. So audio frequency amplifiers. So CE configuration is used in audio frequency amplifiers. So the CC configuration used in impedance matching. CC configuration is used in impedance matching circuits, buffer amplifier. So why? Because output impedance is low. So that's why it is used in impedance matching circuit and buffer amplifiers. So finally, current gain is high, voltage gain is high, power high. So CE configuration is popular. So CE configuration is very popular. So now come to the problems. So we know the output current equations and what are the alpha, beta, gamma relationship. According to that, the problems have to be solved. So this is 2 marks question in GATE. So in a bipolar transistor, at room temperature, if the emitter current is doubled. The emitter current is doubled. The voltage across its emitter base junction doubles. Answer is doubles, halves, increases by about 20 milliamperes, sorry, 20 millivolts, decreases by about 20 milliamperes. So B, C, D. What is the option? See the solution. Right. So here, what is the voltage? What we want to find out, what is the voltage when increase IE doubled. So in a bipolar transistor at room temperature, emitter current is doubled. So IE depends on saturation current. So that means E power VBE upon VT. VBE upon VT. So here IE is equal to saturation current into E power VBE upon VT minus 1. So when minus 1 is neglect, when minus 1 is neglect, it will not affect the operation of BJT. Will not affect the operation of BJT. So that's why you have to write it as the saturation current Is into E power VBE by VT. VBE by VT. So the first emitter current is IE1. So that is Is into E power the first emitter current will be 1 upon Vt. The second IE2 current is IE2 current is saturation current Is into E power VBE2 by Vt. VBE2 by Vt. So IE2 reverse saturation current, same of transistor. Remaining parameters are constants. So only VBE is vary. So here we need this by this. We need this by this. So what happened? Is we get second emitter current larger than the first emitter current due to that reason. So here what you get, E power VBE2 minus VBE1 by VT. The second emitter current larger than the first emitter current due to that what you have to be calculate VBE2 minus VBE1. VBE2 minus VBE1. If we take ln on both sides, VBE2 minus VBE1 is equal to VT ln of 2. We know VT. VT is 26 millivolts into what is the ln of 2? Maybe it is in zero point 0.7. Approximately it is in 0.693. So approximately it is equal to 20 millivolts. So that's why the option is increased by 20 millivolts. The option is increased by 20 millivolts. So the next question is, this is also gate 2 marks question. Consider two BJTs biased at same collector current. Consider two BJTs biased at the same collector current with area A1 is equal to zero point 0.2 micrometer into zero point 0.2 micrometer and A2 is equal to 300 micrometers into 300 or 3 micrometers into 3 micrometers. 300 micrometers. Assuming that all other device parameters are identical, kT by Q is equal to 26 millivolts. The intrinsic concentration is 1 into 10 power 10 centimeter minus 3 and Q value is 1.6 into 10 power minus 19 coulombs. The difference between the base emitter voltage, the difference between the base emitter voltage in millivolts of the two BJTs. That is VBE1 minus VBE2 is what? So in previous case, both are same. But in previous case, this case, the difference is area is given. We know the reverse saturation current of the transistor is proportional to area. Area changes definitely change base emitter voltage. We need to calculate that difference. Okay. So what they are asking to us? So here the collector, so some collector current with area. The collector current. So IC1 is equal to saturation current e power VBE1 by VBE1 upon VT. Here eta is 1. So here IC1 is equal to saturation current is proportional to remaining. So all parameters constant. So A1 K. So here VBE1 by VT. IC2 is equal to A2 of K e power VBE2 upon VT. So in this case, it is cancels. The areas are different. Areas are different. Cancels. So definitely VBE changes. So that's why A2 by A1 is equal to e power VBE1 minus VBE2 upon VT. So what we want to find out? VBE1 minus VBE2. VBE1 minus VBE2 is equal to VT ln A2 by A1. A2 by A1. VT ln A2 is 3 into 3 by, so nothing but 300. 300 by zero point 0.2 int zero point 0.2. 26 ln. So VT means 26. So 300 into 300 by zero point 0.2 into zero point 0.2. What you get? The final answer is 380.28 millivolts. So this is the answer. So it will be asked in 2 marks for gate examination. So next question also asked in gate examination in 2011, the 2 marks question. So for a BJT, the common base current gain alpha is equal to 0.98 and the collector base junction reverse bias saturation current is reverse bias saturation current IC naught is equal to zero point 0.6 microamperes. This BJT is connected in the CE mode and operated in the active region and operated in the active region operated in the active region with a base drive current IB is equal to 20 microamperes. The collector current the collector current IC for this mode of operation is, what is the answer? 0.98 milliamperes, 0.99 milliamperes, 1 milliamperes, 1.01 milliamperes. to find out. So the collector current IC for this mode of operation. What is the mode of operation? Is active mode of operation. So what is the solution for that? So what is alpha? In problem they given to alpha is 0.98. What is the relationship of alpha and beta? So beta is equal to alpha by 1 minus alpha. So according to that, you are able to find out the beta. 0.98 by 1 minus 0.98. How much value you get? So you get the value of 49. So what is reverse saturation current? IC naught is equal to, in problem they given, what is the IC naught? 0.6 microamperes. So IC naught is 0.6 microamperes. What is the IB value? So IB also the given, IB is 20 microamperes. So here IB is equal to 20 microamperes. So according to formula, IC is equal to beta IB plus 1 plus beta into IC naught. So that is, so we have to be calculated. What is the beta value? Yeah, this is the beta value is 49. 49 into, what is IB value? 20 microamperes. So 20 into 10 power minus 6 plus 1 plus beta value is 49. 1 plus 49. So IC naught value is 0.6 into 10 power 6. 0.6 into 10 power minus 6. So here, so these two is 98. So 980 microamperes. 980 microamperes plus 50 into zero point 0.6. So 30 microamperes. So finally you get 1.01 milliamperes. 1010 microamperes. So in milliamperes 1.01 milliamperes. So this is the answer for that. 1.01 milliamperes. So here, so that is the answer for that. So here they are asking all, they have to be given alpha, they have to be given alpha, and we find out the beta. So at the same time they are asking active region, active region. So for that region we want to find out the IC. So implement the IC formula and find out the answer. So next problem. The reverse leakage current, the reverse leakage current of the transistor when connected in CB configuration, when connected in CB configuration is zero point 0.2 microamperes, zero point 0.2 microamperes, and it is 18 microamperes, 18 microamperes when the same transistor is, when the same transistor is connected in CE configuration, connected in CE configuration. Calculate alpha and beta. Calculate alpha and beta. What they given? CB configuration is another means alpha is so CB configuration another. What is this? So this is reverse saturation current. So IC B naught, how much? 0.2 microamperes. సో ఇంకేమి ఇచ్చారు? అండ్ 18 microamperes. So reverse leakage current of the transistor and connected in CB configuration is when same transistor is connected to CE configuration. So CE configuration. So ICE not how much? 18 microamperes. So what is the relationship of ICB naught and ICE naught? So already we discussed in relation. So what is the relation? This is. So ICE naught is equal to 1 plus beta ICB naught. So this is the relation. So you have to be apply that relation to here. So what happened? ICE naught is equal to 1 plus beta ICB naught. So this is the relation. So ICE naught is equal to, so this 1 plus beta will be, write it as 1 by 1 minus alpha. With respect to alpha, how can you write? ICB naught means gamma. 1 plus beta is gamma. Gamma is equal to 1 by 1 minus alpha with respect to. So that's why 1 minus alpha. So 1 minus alpha is equal to ICB naught upon ICE naught. Both you know. So 1 minus ICB naught is 0.2. ICE naught is 18. You get the value 0.988. So this value is alpha. Alpha is equal to 0.988. So this is the alpha value. So how can you find out the beta value? So ICE naught is equal to 1 plus beta into ICB naught. So in this ICE naught, ICB naught, you know. So ICE naught by ICB naught is equal to 1 plus beta. So 1 plus beta. So beta is equal to ICE naught by ICB naught minus 1. So what is the value of ICE naught? 18 by ICB naught value is 0.2 minus 1. What do you get the value? 89. So the beta value is equal to 89. So this is the beta value.